Exponential functions model growth and decay, calculating compounded interest rates, appreciated or depreciated value of properties, population or bacteria growth or decline are some life-related uses of exponential functions. The function has a unique elbow progression as you see on this graph. The function notation defines the behavior of the function using its y-intercept and the ratio of growth or decay. To graph an exponential function, make a table to record the selected x values, y value calculations, y values, and the points falling on the function. Let's begin by choosing random values of x. Technically, you're free to choose any value like negative 2.33. Conventionally, though, whole number values of x are best for convenience. Here, values negative 2, negative 1, 0, 1, and 2 are chosen. The y value at x equals 0 is an essential milestone for any function. This is where the function intersects the y-axis. So make sure to always choose 0 among other values of x. Usually 5 to 6 points are sufficient to graph the trend of the function. Having said that, 2 points are insufficient and 10 points are too many. For x equals negative 2, plug in negative 2 in place of x in the given function. A common mistake done is multiplying 0.5 times 2, then raising the product to the power. The right way to evaluate this function, however, is to raise the base 0.5 to power negative 2 first, then multiply that times 2. If you're fluent in working with fractions, go ahead and complete calculations manually as shown. Otherwise, use a calculator. When x is negative 2 on this function, y is 8. Write the coordinate point negative 2 and 8 in the last column. Repeat the same steps, just using a different value of x one at a time to find its corresponding y value. On a graph paper, draw the x and y axis. Plot all 5 points on the coordinate plane. Finally, connect the points. Note that the y-intercept on the graph is the same as a on the given function notation. For now, take note that this function is located above the x-axis. Let's try another example. Graph the function y equals negative 4 times half to power x. Obviously, this is an exponential function since the variable x is the power. So we expect an elbow-like graph. Set up the table, choose random x values. In this example, the same 5 values are used from the last example. Start by plugging in negative 2 into the function. Raise half to power negative 2 first, then multiply that times negative 4. The y value at x equals negative 2 is negative 16. Record the coordinate point and continue on with the remaining x values. Plot the points on the plane, then connect them. The function intersects the y-axis at negative 4, which is again the same as a. This function, though, is located below the x-axis. The sign of a determines whether the function is located above or below the x-axis. If a is positive, then the function is called a positive function and appears above the x-axis. On the contrary, if a is negative, then the function is below the x-axis and described as a negative function. It's important to recognize that a positive function is not necessarily an increasing function. In other words, a negative function can be increasing. Look at the top red function. It's positive but decreasing because as values of x goes from left to right or from small to large, the y values decrease. Therefore, the top graph belongs to a positive decreasing function. For the blue function, it's negative and increasing. Again, notice how the values of y increase as values of x increase. Together, a and b dictate whether a function increases or decreases. For the function on the left, b is 2. Raising a number greater than 1 to increasing powers magnifies the product. When multiplying that large product times a positive a, like 0.5, it maintains the incline of the function. On this graph, the combination of a greater than 0 with b greater than 1 makes y values increase as x values increase. Let's inspect this function. A is still positive, but b is a fraction. Raising an improper fraction to increasing power significantly shrinks the value of the product. In other words, the greater the power is, the smaller the fraction becomes. In this case, as x goes from left to right, y values decrease. Let's look at another example. The exponential part of this function is magnified since b is greater than 1. However, multiplying a substantially large positive number times a negative number, like negative 0.5, drags down the value of the entire function. Therefore, this function is negative and decreasing. For this last one, b is an improper fraction, which its values decrease as the powers increase. Multiplying substantially small positive fractions times negative numbers like negative 0.5 actually increases the overall value of the product, simply for the fact that negative numbers with the least absolute values are greater. For example, negative 1 is way greater than negative 20. For this reason, this function on the right is negative and increasing. Let's try to describe the trend of the following functions without utilizing their graphs. The first function has a negative a, then it should appear below the x-axis. However, the function is decreasing since b is greater than 1 and a is negative. Next, this function is obviously positive. It's also decreasing since b is a fraction between 0 and 1. This one here is also located above the x-axis but increasing since b is greater than 1. Finally, this function is definitely negative, but because b is between 0 and 1, the function is increasing. So far, we have been looking at the parent exponential function y equals a times b to power x. Like any other function, vertical translation or shifting is possible when altering the function. A constant c added to or subtracted from the parent function drags the y-intercept up or down, respectively. For this function, a 0 is not written, but understood. This is equivalent to the parent function. A in parent functions signifies the y-intercept. So here, 0.25 is the y-intercept. For function g, c is 3. By comparing functions g and f, it's apparent that the y-intercept for function g in green has been moved up vertically 3 units. The y-intercept on the original function f was 0.25 and becomes 3.25 for function g. Note that a in the variation function g does not reflect the y-intercept for this function. Only parent functions with c equals 0 have their y-intercept equals a. This rule does not apply for functions with c does not equal 0. Similarly, h is a variation function of f with c equals -1. Again, the y-intercept has been dragged vertically, this time down 1 unit. Exponential functions have unique features that define each function. Let's look at this graph of function y equals -5 times 3 to power x. Again, c for this function is 0. All exponential functions have horizontal asymptotes, which are imaginary horizontal lines to which functions approach but never touch or cross. The equation of the asymptote is y equals c. In this case, since c equals 0, the equation of the asymptote line is y equals 0. Or, in other words, the horizontal asymptote for this function is the x-axis. Note that the graph of the function in blue seems to meet the dashed asymptote line. However, substituting a very small value of x like -100 in the function gives an extremely small y value but never gives a 0. Domains of functions are the set of all possible x values. Since any value on the x-axis can be plugged into the function as an input, then the domain interval is basically all possible real numbers ranging from -infinity to +infinity. In general, domains of all exponential functions have this same interval. The range of a function is the set of all possible output values, in other words, the possible y values. Since exponential functions have asymptotes, then they always have either a maximum or a minimum y value. For this graphed function, the y value can be infinitely small but cannot touch or exceed the dashed asymptote line y equals 0. The range interval is -infinity to 0, excluding 0. The y-intercept of a function is the point where the function intersects the y-axis. The x-coordinate for this point is always 0. To calculate the y-coordinate of the point, simply plug in 0 for x and evaluate y. Remember, any number raised to power 0 is 1. So here, 3 to power 0 is 1, then 1 times -0.5 is -0.5. The y-intercept point is 0 and -0.5. Alternatively, a in this parent function directly gives the y-intercept. Finally, the x-intercept is the point where the function intersects the x-axis. Looking at the graph, it's obvious that such point does not exist because the asymptote for this function happens to be the x-axis itself, which means that the two functions will never meet. Now let's identify the key features of this function without relying on its graph. First, the equation of the horizontal asymptote is y equals 2. The y-intercept of this variation function can be found traditionally by plugging in a 0 in the given function. A shortcut for this calculation is to simply add a plus c, which in this case 0.75 plus 2. The y-intercept point using either method is 0 and 2.75. Now this part can use some imagination to visualize the function without graphing it. Compare the y-intercept 2.75 to c, which is 2. Since the y-intercept point is located above the asymptote line, which itself is above the x-axis, then this function must be located above and will never meet the line y equals 2, which leads to conclude that it's impossible for this function to intersect the x-axis. The domain for this function can be any real number, so the interval for the domain is -infinity to infinity. The range has a minimum value of 2 and can have infinitely positive y values. The interval for the range is all real numbers between 2 and infinity, excluding 2. Now let's bring in the graph. All features concluded from the function notation must match the graph of the function. Let's look at function h equals 0.45 times 0.5 to power x minus 3. The first identifiable feature is the equation of the horizontal asymptote. It's y equals -3. The y-intercept point is 0 and -2.55. Now compare the y-intercept -2.55 to c, which is -3. Obviously, the asymptote line is below the x-axis, and the y-intercept point is right above the asymptote but below the x-axis. This means that this function surely intersects the x-axis. Calculating the x-intercept point usually involves working with logarithms, like this function, which is out of the scope of this lesson. The domain of the function h is all real numbers. The range does not have a maximum cap, but cannot be or go below -3.